In this video, we're going to look at pieces of evidence for the theory of relativity. And the main one we're going to focus on is how muons provide evidence for time dilation, which is a prediction of the special theory of relativity. And this is a result of two experiments, one that took place in 1940 and one that took place in 1963. So in terms of scientific discoveries, still relatively recent for us. So I'll start by just kind of reading the introductory paragraph. So it says, muons are highly unstable elementary particles that are created about 7,000 meters above the Earth's surface as high-energy cosmic rays hit the nuclei of atoms in the air. Being highly unstable, a muon will quickly decay into an electron plus a neutrino and an antineutrino. Rossi and Hall found that muons have an average lifetime of about 2.2 microseconds. With such a short lifetime, muons should not be found near the surface of the Earth because they wouldn't have time to get there. But muons, however, have been found near the surface of the Earth. And a later experiment by Frisch and Smith found that muons actually travel near the speed of light, which would give them enough time to reach the Earth because they travel at relativistic speeds. So, we have part A, B, and C, and I'm actually going to do part A, B, and C on a separate sheet of paper here. But part A says, using the equations of classical mechanics, calculate the distance a muon can travel during an average lifetime. So let's start by just drawing a picture here for a minute. So I'm going to call this the, let's see if I can get a little bit clearer. All right, I'm going to call this the Earth. And muons are created way up here above the surface of the Earth. So we'll draw what we are going to assume to be muons. And this distance, this average distance, is about 7,000 meters. So when part A says to use classical mechanics, that really just means don't use relativistic equations. So the special theory of relativity assumes that everything is traveling at a constant velocity. So therefore I'm going to use the constant velocity equation. And Frisch and Smith found that the velocity of muons is 2.994 times 10 to the 8th meters per second. And we know that their lifetime is 2.2 microseconds, which is 2.2 times 10 to the negative 6, but I'm going to write that number out of scientific notation. So it would be 0.1, 2, 3, 4, 5, that would be my 6th, and then the extra 2. And so the question is, how far would they be able to travel? So we can number crunch this one. Let's see if I don't know if my calculator will show here. So we have 2.994 to the 8th times 0.1234522, 658.68. I'm just going to round that off to 659. So about 659 meters. So because they have such a short lifetime, as they start to fall towards the Earth, after 2.2 microseconds, they disappear, and they will have only fallen about 659 meters. So they would never reach the surface of the Earth. But the next set of experimenters found out that, or I guess supposed, that relativistic time might be coming into play. So part B says, if the muon is traveling near the speed of light, calculate the average lifetime of a muon as viewed from the Earth. So we're going to use relativistic time, and we're going to actually solve for this t. So we know that the lifetime of a muon, we're just going to kind of pretend that the muon is in like a invisible spaceship. And so his time in his invisible spaceship is 0.00000022. That's like his lifetime. And on the bottom, we're going to have 1 minus, then we have our 2.994 times 10 to the 8th You're going to square that and then over c squared. So we're solving for t, how much time would pass on Earth from the perspective of Earth. So I'm going to start with my 2.994 to the 8th, and I'm going to square that. Divided by 3 to the 8th, and I'll square that. 1 minus that answer. Then I'm going to square root that answer. Then I'm going to take the time, 0.1234522, and I'll divide by that answer. And this is the amount of time that would take place as viewed from Earth. So 3.48 times 10 to the negative 5. So 3.48 times 10 to the negative 5 seconds. Let's write that out of scientific notation. So that would be 0.1234, that would be my fifth, 48 seconds. So that looks like it's not very long, but this number is bigger than the number that's taking place in the spaceship. Remember, our Muon is going to be like in an invisible spaceship. So this is his very short lifetime, but as viewed from the Earth, his lifetime would be longer. Or if I said it in a different perspective, this is the lifetime of a Muon, but he knows when he gets to Earth, more time will have taken place. So if this is true, then the question is, how much time or how far could he travel during his relativistic lifetime? So I'm going to say velocity is distance over time. And so I have whoops, this is off my screen here. 2.994 times 10 to the 8th. So as viewed from the Earth, the lifetime of a Muon would be longer. So that's going to be the 0.0000348. And how far would he be able to travel? So to solve for D, I'm going to multiply those two numbers together, and my time is still on my screen. So let's just multiply by the velocity, 2.994 and we find out that the Muon could actually travel in his relativistic time 10,420 meters. Distance is 10,000, I rounded off to 420 meters. Obviously more than enough time that they're created 7,000 meters above, and they have time to travel 10,420 meters, more than enough time to reach the surface of the Earth. So this experiment, or the combination of both of these experiments, provided proof of time dilation. And again, if time dilation is true, that would lead to a higher probability that other pieces of the special theory of relativity might also be true. So let me tell you another short story that may or may not be in the links that I provided you. So another piece of evidence that they did relatively recently, I don't remember when, maybe the 1970s, I don't know. They took two atomic clocks, and an atomic clock is just going to be, we'll call it a digital clock that's accurate to like many, many, many decimal places. So we have two atomic clocks that are synchronized with each other, and we take them both to the airport. So one of them is going to stay at the airport, and the second clock we're going to put in an airplane and fly the airplane around the world as fast as we can. So we did that. The airplane comes back, and they take the two clocks out, and the clock that was in the airplane, the time went by more slowly, and the clock that was left at the airport, that was left on Earth, the time went, more time had actually passed. Again, just like the spaceship Earth scenarios that we've talked about, and again, the difference was not great. It was 0.0000 something, but enough that it could be measured with our current speed of our airplanes on a piece of technology clock that we have now. So the purpose of this assignment is for you to do a little investigating on your own. I'll be honest, some of these experiments are kind of difficult to understand, and but I just want you to read a couple more of them to convince yourself that, wow, it's highly, highly likely that special theory of relativity is true, and that has a lot of implications for physics. So I want you to, for page 2, I want you to pick 3 more pieces of evidence. And you can find these pieces of evidence by maybe on these links that I give you on page 1 here. And if you just want to Google evidence for special theory of relativity, go for it and see what you find. And so you don't need to give me the website, but you just need to give me the name of the experiment, give it a brief title, like the one that I just did here. If I had to give this a brief title, I would call it muons. And then give me an approximate date of when we have found this evidence, because many of these things are relatively recent. In fact, one of them is as recent as the year 2016. And so give me the dates, okay, so we can see that we're still discovering things. And then just give me a brief description. You don't need to fill up all the lines, a couple of sentences. If I had to summarize this, I could write all of this, or I could just write down that muons should not be able to reach the surface of the Earth, but if they traveled at relativistic times, they would reach the surface of the Earth, and we have detected them on the surface of the Earth. Therefore, this experiment shows that relativistic times are most likely taking place. So just a quick summary of what you found there. And I hope you find the evidence rather interesting also. All right. I hope that helps you finish up the last assignment of our unit, and look forward to seeing you soon.